Right, so we're going to spend some time to just kind of go back over a bit about lenses, so that we can have a bit of idea pertaining to that. All right. See, as you would imagine, there are two different types of lenses, convex and concave lens, or in some case we say converging or diverging lens. Those are generally the two types of lenses. Lenses are generally some type of transparent materials that assist with refracting light. Yes, and as you can imagine, we use these to correct different eye conditions. It's important to note that depending on the thickness of the lens, that will determine what we call the power of the lens. All right. So if the lens is much, much thicker, it would generally have what we call higher power, so to speak, which is just the amount to which it is able to refract light, really. The unit for measuring that power of a lens is called diopters. And how we really find the power of a lens is just 1 divided by the focal length. And I'll show you where the focal length is. So if you want to find the power of a lens, what you simply need to do is to make sure you know the focal length. And the focal length is simply the distance from the center of the lens, so the optical center, to the point where the light rays converges. So here we have a thicker piece of lens, yes? The thicker the lens is, the faster and the quicker the light rays are going to refract, which means that the focal length is going to become shorter, okay? Having a much shorter focal length, right, tells us that the lens has a larger power, or the power is much, much stronger, right? And as we said, how you find that out is by taking the formula that says P is equal to 1 upon the focal length, which is F. And then, of course, your unit is going to be diopters. This one is a much thinner lens, which means that the light rays are going to take a much longer time before they converges. So if we measure the distance from the center of the lens to where they converges, that is considered to be the focal length. This focal length is much longer than this one. Therefore, this lens has less power. All right. Bear in mind the lens equation. This is possibly from your CSEC knowledge, but it still applies here. 1 upon F is equal to 1 upon U plus 1 upon V, where U is your object's distance, Generally speaking, the objects are always located on this side, mainly, yeah? So the object is always on the left side, which is technically in front of the lens. So this portion here where the light rays are going towards the lens is called the front of the lens. And if you were to measure the distance from the optical center to where the object is located, then that will be considered as your object's distance. It can be in meters, it can be in centimeters, you name it. All right. So I will refer to that distance as U. All right. Now, as you can imagine, depending on the type of lens, we can produce different images, you know. So like with a converging lens, depending on where the object is located, you can either produce a real image, yes, or you can produce a virtual image in some case, and you can also produce a upright image and so on, or inverted image. So once that image is formed, it has some distance away from or from behind the lens, really, right? So you can measure that distance, and that distance would be your image distance. That symbol is V, as you can imagine. I want to point this out to you, that when we're dealing with converging lens. When we're dealing with converging lens, we find that the image distance is always positive. Okay, so we're saying that V is always positive. Same thing as the object's distance. So the object's distance is always positive as well. When you're dealing with diverging, on the other hand, diverging lens, we find that the image distance is going to be negative. Okay, image distance is going to be negative. The object distance will be positive. The focal length for the diverging lens is going to be negative as well. Right, but I'll just confirm quickly on something. But the focal length for sure is going to be negative. All right, so it's going to be negative F for diverging lens. For the converging lens, focal length is positive. Focal length is positive. All right, that's always the case. So in essence, you could almost put it to say that for converging lenses, all of those parameters are positive, and you can also talk about the height and so on as well. So the heights would be positive. But for the diverging lens now, there are two things that I'm gonna confirm, but I know for a fact that the focal length has to be negative. So for the diverging lens, the focal length has to be negative. But I'll check that quickly for you. But in the meantime, magnification, that just speaks to how ratio of the image versus the object, right? How large it has been, how small it has become, etc. Right? But in most cases, magnification speaks to a ratio of the size of the object, right, versus the image. And how we can find that? We can find that in two ways. And I want you to pay attention keenly. So M, which speaks to magnification, it doesn't have a unit. We can take our image distance, divide that by our object's distance, and that will give us the magnification. Another formula that we could use for magnification can be the image height divided by the object's height. And what you would, if you get a graph, you would just use your ruler to measure the object's height vertically upwards, and if the image is down this side, you measure it as such. Okay, you just measure the centimeters on the graph or whatever. So that would be your height from the principal axis. So what I want you to keenly pay attention to here is because sometimes they can tie different things together. So what if you weren't given all the information or whatever? They want you to find the object's distance, but maybe you know the image distance. Then you could link these two formulas together. Since they're equal, you could link them together and transpose to find out what your image distance is or your object's distance is. It depends on what you're trying to find. So you're not limited to the information that you can find when you're dealing with these problems. So make sure you pay attention to this, right? That you can actually use that to figure out some unknown thing. All right. But if there are any questions, please let me know. All right. So I'll just make the correction just now as it pertains to what I was telling you about. Give me 1 second. Just to copy this. I believe you might have your study guide, so you could. Right. So this is what I want you to quickly look at. So let me just correct something. So when it comes on to the focal length, yes, for the converging lens, that will always be positive. For the diverging lens, it's going to be negative. Whenever we have real objects and real images, yes, those are considered to be positives. Okay, those are considered to be positive values. But whenever we have like virtual objects and virtual images, those distances are considered to be negative. All right. So this part is quite important when it comes on to the virtual image, because as you know, depending on the position of the object, you will get a virtual image sometimes. So that virtual image, the distance, the image distance would be negative, right? If we were looking at a virtual image, okay? But I must just say that you can get a virtual image with a converging and a diverging lens. So in the case that it is a converging lens and we get a virtual image, then we consider that distance to be negative. The image distance or the image height will be negative. However, the object's distance will be positive because it's a real object, all right? If it's a real image, those are considered to be positive values. Are there any questions?
No, sir.
Have you been studying this aspect of the syllabus pertaining to this?
I haven't reached there yet, sir.
Okay. All right, just some few definitions that we should pay attention to, and that starts off with accommodation. All right. It's important to note that the lens that is in your eyes generally tends to change its shape to allow light to be focused on the retina. So sometimes the lens will become thickened or it will become elongated just to accommodate the light rays that are coming towards the eye. So that is considered to be accommodation. So accommodation is just the shifting of the lens, yes, so that it focuses images properly on the retina. So that's just simply what it is. So bear that definition in mind. There's something what we call the near point, all right? If you were to take your hand without blinking and bring it all the way towards your eyes, you'd find that your hand becomes blurry, all right, as you approach your eye very closer and closer. What we have come to realize is that our eyes have a certain distance, right, from the lens, right, where if we go less than that towards your eyes, the eye cannot focus or it cannot accommodate that image anymore, sorry, or that object anymore. Meaning, just like you take your hand, yeah, and you bring it closer to the eye, you realize that it gets out of focus. That means that your hand has now passed the near point, okay? So generally speaking, the near point of a normal eye is 25 centimeters. Anything beyond that, right, generally becomes blurry because the eye cannot accommodate, right? The lens cannot adjust itself any further to allow the image to be properly formed on the retina. Now, there are some eye conditions that forces your near point to be larger than the 25 or less than the 25. So a person's near point can be shifted. And this is now where the different lenses kind of comes into play to help to correct that. So a person who has a very far near point, that person will not have the ability to read objects that are close to their eyes, right? And so you find that they would have to use a particular lens, yes, to assist with that. Those persons would be generally farsighted, and you can correct me if I'm wrong, but I believe farsightedness is when you can see distant objects, but I'll go through it from the notes that I have here. And so you would need a particular lens to correct that so that you can then see we call closer objects to you. Anyways, there's something we call the far point as well. So we have the near point and we have the far point. The far point is the furthest distance that a normal eye can see an object in a distance, really. All right. So the furthest you can see a distance, see an object, that distance is considered to be your far point. And in most cases, the far point for a normal individual is considered to be infinity. Okay. All right. Let's just look at different common, different, what we call eye defects and how we can go about correcting them. These are general questions that they can ask you. So you have short-sightedness, which is called myopia. And in some cases, we say nearsighted. Now, what is happening with the eyeball is that the eyeball is generally a bit too long, yes? So the eyeball is a bit longer than usual, okay? And so, or we could say that the lens is too thick. So there are two things that can happen. Whether the eyeball is too long or the lens in the eye is too thick. This is generally linked to short-sighted. And so you find that persons with short-sightedness are able to see objects. They're mostly able to see objects closer than 25 centimeters, which means that their near point is less than 25 centimeters. Okay. But they cannot see distant objects, right? So they cannot see distant objects. To correct this situation, we have to use diverging lenses. All right, so this is what the setup would look like. This is what the person without the lens is seeing. So when they're looking at distant objects, because the lens is too thick, the light rays are converging before it hits the retina. Okay, we want the conversion to take place. What do you call it? We want it to convert on the retina. But if it is, if the lens is too thick, or if the eyeball is too long, then you find that that process of converging of light rays will take place before it reaches the retina. Okay, so to shift that process or to change that, we have to use a diverging lens. So the diverging lens now would help with diverging the light rays a bit, pushing them further apart as they approach the eyes, so that it can adjust it in such a way that it falls completely on the retina. And that person will now be able to view objects from a longer distance. But as we said, these persons are able to see objects closer than 25 centimeters. Is that understood?
Yes, sir.
All right. For long-sighted, yeah, this is considered to be hypermetropia, and it's just kind of like the opposite of short-sighted. In this case, eyeball is too short, or the lens is too thin. All right. And in this case, the person can see distant objects but cannot see near objects. When the person is viewing near objects, what we find is that those light rays will fall behind the retina, or the light rays would generally want to converge behind the retina. To fix that, we have to use a converging lens. You have to use a converging lens to fix that. So what the converging lens will do is to take the near objects and forces them, add a bit more converging to them, or refract it a bit more before it enters the eye, so that it can fall on the retina. So those are some of the things you can be asked to write on. In addition, they can ask you to talk about other eye conditions such as astigmatism. All right. So it says that this happens when a person's cornea or lens is shaped somewhat cylindrical rather than being perfectly spherical. So that allows the persons to see some type of blurry images. Okay. So just remember what astigmatism has to deal with is when the person's cornea or the lens is, rather than it being spherical, it's more kind of a cylindrical type of lens. And so it does not kind of make the refraction, because in fact, your cornea is the first place where refraction start taking place, right? So if that's the case, then you're not going to be able to can actually converge or refract the light ray in a more perfect way, or in a better way, as you can imagine. And so the light rays are going to end up being blurred, because when the light rays hit the cornea or hit the lens, you find that it will refract in different locations, and that will help with, or that will cause the image to be a bit distorted when it reaches the retina. Here we have another one called cataract. All right. This is when the lens becomes opaque, and it says that the vision becomes blurry as the milky lens scatters the light itself. All right. Of course, if you can find some more information pertaining to these things and how we can treat them, that will be good for you when you're revising, just so you can add a bit more information to this if you're asked to write on it. Field of depth. Field of depth is simply a range of distance over which the image by a camera is seen acceptably sharp. So it's a range of distance over which the image, I'll see if I have a picture to show you. This one is a little bit, yeah, the field of depth is a bit, it's not so easy to explain. But if you can remember what it is, then that will be good for you. But I'm seeing here, it says that a range of distance over which image by a camera is seen acceptably sharp. Please just make sure you research it a little bit more, so you can actually you need to probably identify that on a camera, that then you probably should be able to can identify that, right? The depth of field. All right, so we're gonna look at some questions right now as a way of recapping. If you have your study guide, please go through it and look back at some of those questions pertaining to lenses and all of that. All right, but now we're gonna just look at some questions regarding lenses and some regarding some other things. Yeah. So let's see how best we could answer this together. So long-sightedness is an eye defect that affects many persons. Explain using suitable optical sketches how long-sightedness occurs and how it can be corrected. Feel free to share whenever you have come up with something pertaining to that, yeah?
So can I try?
Yeah, of course, go ahead.
Okay, so long-sightedness takes place when the eyeball is short and the light rays that are passing like through the eye, through the cornea and the lens focuses behind the retina. And I think I can answer this on the screen, but or
So which objects are affected? Which objects are affected when the person is long-sighted?
um objects that are close to them.
Objects that are close, yeah. And you said it falls behind it, yes? Behind the retina?
Yes, sir.
All right. And the eyeball is short. So how do we correct it?
By using a converging lens.
By using a convergent lens. And of course, you will be asked to draw how it is corrected. All right, yeah, very good. And of course, just drop the convergent lens in front, and that should now adjust it.
Sir, my mouse is not that good.
You almost finished.
Yeah.
All right, yeah. Although it almost look like it's diverging right here still, but you know, I get the picture. So, you know, when it comes like this, you'd want to kind of bring it down and not out like how you did it here. But I don't know how sensitive your markers will be.
No, sir, it was my mouse. I can't
Oh,
control it
oh,
very.
oh, oh, oh. Right. So just make sure that you kind of make an effort with, and this is for everyone, that they're literally seeing a level of what do you call it, converging. You know, the light rays. But I get the whole picture. All right. Good. All right. So it says now use array diagram to show how focus images are formed in a magnifying glass. Anybody think we know the answer to this? So magnifying glass. Yeah,
Oh.
sure. Go ahead.
Something like I have like an image and then and then this is the lens. I can't draw the lens properly. I can't. I don't like
All right, I'll show you. Let me show you. Delete that for me.
it takes time. I don't know. Oh.
So you know, when I looked up this thing recently, it wasn't as difficult as how I thought it was. So for the magnifying glass, it uses a converging lens. However, the object rather, let's take for example a car, right? It is placed in front of the principal focus. Right, so this would be like your principal focus. If you put any image in front of the principal focus for a you call it a converging lens, the image is going to be virtual, and that's what a magnifying glass gives us, right? So that's when so what you would need to do is to obviously draw a light ray that go towards this side. You're gonna have to obviously make sure that you have your principal focus here again, light ray passing through this one. You're gonna need another light ray that runs through the center of the lens. And what you're gonna do using your ruler and everything, you're gonna extrapolate using some broken lines. And wherever those broken lines converges, that is technically where the image will be. All right. So your image is going to be located around this region, magnified, because remember it's a magnifying glass. So that's technically what I'll just quickly show you what it looks like in the study guide, which is practically the same thing. So let's see if we can add this. Right, so this is technically what it looks like, just as how I showed you. So it's like your your object has to be in front of your principal focus. All right. And then from there, so now you would, any object that is in front of the principal focus is going to produce a virtual image. And that is technically what we would be seeing, yeah? So if you can make note of that, that'll be good. All right, we have it.
Yes, sir.
All right. The others, are we okay?
Yes, sir.
All right, perfect. Now let's just do a bit of calculation. It says an object is placed 20 centimeters from a converging lens of focal length 18 centimeters. Now, I want you to pay attention. If the question had said diverging lengths, then you automatically should make sure that your focal length is negative. So those are a bit of key things you should pay attention to. But it says it's placed 20 centimeters from a convergent length or focal length, 18 centimeters. All right. Now they want you to calculate the position of the image and its distance from the lens. You think we can do that?
Yes, sir.
All right, give it a try for me. All right, what we getting? At least for the image. Well, either one, what that you want. Which one you want to tell me the answer for first?
Sir, I got negative 36.
Yeah, negative 36 centimeters for which variable?
For the image distance.
Right, right. Okay. So what about now the position? I think they say they wanted to determine the position. Um,
So when they mean position, what do they mean? Like if it's real or virtual?
uh, all right. No, I'm thinking, yeah, whether they want you to determine it. Because you probably the position could speak to the height of it in a sense, right? That's what I'm thinking. It could be speaking about the height, but to be on the safe side, the position in this case would be upright per se, but you could go ahead to calculate the height. But I think they're just speaking about you stating whether it is upright for the most part. But if you're not sure, then you can give more than one answer to just leave the scope open for them to mark the correct one. All right. So this is what we'll be expecting to use, is to use the lens equation. By the way, ladies, this equation can also be given to you as a graph, and then they can ask you to plot this, plot that, and find this, you know, whether to use a gradient to figure out whatever. All right. So bear those things in mind. So we're trying to find V. So 1 upon F minus 1 upon U is equal to 1 upon V. We have 1 upon 18 minus 1 upon 12. And I guess in this case, you don't necessarily need to convert the centimeters, because at the end of the day, your answer will be in centimeters and you can work with that. So when we work out all of this, we end up with negative 1 upon had you said negative, young miss? You had said negative?
Yes, sir.
Okay, okay, good. Right, so we just need to take the reciprocal now, which tells us that V is equal to negative 36. Having said that, I think that completes that part of the question, other than the fact that we need to state that the image is going to be upright. All right. Now they ask you whether the image is virtual or real. So remember, you were asking if you're talking about whether it's real or virtual. Like, you can now know that that wouldn't work for the position in that case. And still, we might need to go back and talk about the position again, because based on these questions now, you know that what we were saying around there wouldn't work, because they're asking about the orientation. The orientation now would be speaking about upright or inverted. So we need to go back a bit to understand what they mean by the position of the image. Anybody have any idea as to what they might think about the position, or what they might mean? Okay. Position of the image in front of the lens. In front of the lens. That's what it means.
Oh, so that's all it means?
That's all it means, yeah.
Oh,
okay. You know, sometimes the image can be formed on this side, right? And then sometimes it formed over here. So especially when you're dealing with the virtual images. So the position is that it's in front of the lens. If it was over this side, then we would say it is behind the lens. So it is in front of the lens. In this case, it's a virtual image. Virtual image. And if they then ask you to calculate the magnification, magnification is equal to V upon U. Remember now, yeah, we can just go ahead and put the negative 36. And the negative just kind of tells you that the image is a virtual image. I think this was 12. So the magnification in this case is going to be -3. Okay. And it says, hence its orientation. Orientation is upright. So when we talk about,
Wait, so
yeah.
is the 12 negative?
Sorry. My apologies. So 12 wasn't negative, sorry. right? So when you hear we talk about orientation, it just speaks to whether the image is upright, meaning that it is standing in the same way as it was as an object, or it can be inverted, you know. Inverted would be like when it is below the principal axis. Sure, go ahead, please. All right. So that is what the inverted part. Inverted will be on this side, you know, where it's like upside down. Once it is on the same side where the object is, so imagine that is where the object is, and the image is on the same side, then we say it is upright. Let's just pray and hope that it doesn't get more complicated than this. I'm sure it won't, but we are praying, yeah? For you, we are praying. All right. No, just a projectile motion question. I mean, these shouldn't be so difficult at the end of the day, but it can be difficult sometimes if we fail to remember a few things. Once you have vectors that are at an angle, you know, it ends up having two components, vertical and horizontal components. So here we have this 300 meters per second velocity vector, and it will have its horizontal component. We can call this v of x. We can have v of y. Okay. Of course, we can figure out what they are based on where this angle is positioned, 40 degrees. The angle is positioned beside the horizontal side, which is going to be cos. So we're going to say 300 cos of 40. Likewise, this is going to be 300 sine of 40. With that being said, we can calculate what they want us to calculate. Calculate the initial horizontal component of the missile's velocity. So, I mean, once we have that, we can work it out, you know. Tell me what the value is for.
229 meters per second. Oh, 229.8 meters per second.
229.
0.8.
All right, so here what? Let's just keep it as 230, yeah? Since these are, in essence, you don't have any decimal points, let's not include any decimal points, okay? That will be speaking that it is more precise than what we started out with. So let's just stick with that. So you just round it up to the nearest thing. All right. Okay. So that gives you 2 marks, you know. Now this says by negligible air resistance, all right, determine the horizontal range of the missile. You see, in these cases, we have what we call like is it a parabola, right? And whenever we have the parabola type of projectile motion, meaning that it starts at the same level and ends on the same level, meaning that it starts here and come back down to the same ground level, that type of system is the parabola type of projectile motions. And in such cases, the distance from where it starts to where it stops is considered to be the range, okay? So if they say the range, they're talking about the horizontal distance from where it starts to where it stops. All right. This, you will only hear them talking about the range whenever it is a parabola like this, okay? That's the only time you hear them talking about the range. If they just ask you about the horizontal distance, it doesn't mean that you're really finding the range, but you wouldn't call it the range. The range is only applicable to horizontal distance. And that, in this case, horizontal distance, I must just tell you again that there's only one equation that you can apply when dealing with the horizontal component or the horizontal distance or the horizontal aspects of any type of projectile motions. And that is the equation for speed or velocity. Velocity is equal to distance over time, or we can say speed is equal to distance over time or whatever, right? That's the only equation you can apply in this case. Now the range would be the distance, okay? So we can just transpose and we get v times the time. They told us the time for the flight, which is 39. I would just times that by the horizontal component, which is the 230, right? And that would give us the range. So how far do we get it?
Eight 8,970 meters.
All right, thank you. Now, just another projectile type of scenario. So a student standing on the top of a cliff throws stone with an initial velocity vi at an angle of theta to the horizontal. Okay. Now they want you to write expressions for the initial vertical and the horizontal components of the velocities. All right. So in essence, they want you to do the same thing what we did previously, resolve the vectors, but you're not going to put any values. So if they say with respect to v, xi, and so on, right? Just make sure that whenever you're writing those things, it is reflected there. So like for the vertical component, v, y, I, that will be the initial vertical component. That's going to be vi sine of theta. Then vx of I is going to be vi cos of theta, you know? So don't be confused if you're not seeing any values, just do what you normally do, all right? The thing is, you know, they're not going to do something that you're not really familiar with, just kind of stick to the same thing where you're kind of used to. But I try to go flip the switch and, you know, I try to do some crazy stuff whereby it doesn't really require it. Better you put back what you're kind of used to than for you to invent something new in the exam. You hear me I say? So they will use some tactics to kind of trick you a bit. So these are obviously past paper questions that talks about telling us what is accommodation, astigmatism, and cataract. So it will be good if you can remember these things, obviously. But if anyone wants to give it a try, then I would appreciate your effort.
So can we answer?
Yes, yes, yes.
Okay. So accommodation is the ability for the lens to change shape so that it's able to bend the light towards the retina.
Mm-hmm. Anybody's want to give it a try for astigmatism? Thank you. Astigmatism?
Sir?
Go ahead, please.
So this happens when a person's cornea or lens is stopped somewhat cylindrically rather than being perfectly spherical, and the person sees blurry images.
Right, right. So it's when it's shaped, when it is shaped cylindrical, yeah? Perfect.
Yes.
All right. Is Courtney back? Not Courtney, Kimberly. Kimberly's back. You know, she said she was going to go somewhere. Cataract. Give it a try, somebody.
I can do cataract.
Go ahead.
It's when the lens of the eye become opaque, so vision becomes blurry as the milky lens scatters light.
Yeah. So, you know, it's the lens that is being affected here. And then, of course, it's like you're kind of, the lens should be a bit transparent, but, you know, due to whatever thing that is happening inside of the eye, then that's what results in it being opaque. So therefore, the light is not able to be refracted as well. So it is more being bumped off or scattered, as you can imagine. So hence, the image is going to appear blurry when you see it. All right, it says using lenses with a power of 2.5 diopters in her lenses, sorry, in her glasses rather, a woman can comfortably read a book held 25 centimeters from her eyes. Now, it has with the aid of a diagram explain the eye defects from which she suffers. And then you want to determine the near point. That is the distance from her eyes where she can see objects clearly without her glasses.
So does she have long-sightedness?
Why you say she have long-sightedness?
Because it says that she needs a lens so that she's able to read something. Oh wait, not from her eyes. My bad. That's short-sighted. Here we go.
So she has on her glasses, yeah? And the glasses is allowing her to be able to can read something at 25 centimeters from the eye. Hello. Hey, I'll call you back, yeah? Good. Yeah, that question is kind of tricky still enough. I'm not gonna lie, it kind of tricky. It was a bit tricky. So let's see. So she has on her glasses, Zine, and that glasses is allowing her to be able to can read something that is 25 centimeters, which means that before that, she wasn't able to read something at 25 centimeters. Would you agree? So if now with the lens, she's able to read something at 25 centimeters, which is the near point of an actual eye, yes? That give us the impression that she wasn't able to do so, which would give us the impression that she was farsighted. Because farsighted people are able to read distant things, but cannot see things close up. Can we agree on the points that I'm making? Let me know.
Yes, sir.
Yeah. 'Yeah. 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 Right? Having said that, we now know that she is farsighted, given that before, or with the lens rather, the lens is allowing her to read comfortably at the perfect near point of a normal eye. And I mean, that is the closest that an object can get to the eye. So therefore, before that, she wasn't able to view things at 25 centimeters, which tells you that she cannot see near objects. So that would imply that she is farsighted. That means that she can see things that is further apart, or we can say she's long-sighted. So you would draw, obviously, your diagram and everything to, in a sense, figure out the that's the correct thing, yeah, with the lens and everything. And you put a bit of explanation behind of it. So I think we know how you correct correct long-sightedness. We use a converging lens. We agree? Use a converging lens to fix that condition because the eyeball is too short, so the light rays are converging behind of it, the near objects. Now, the part now that can be a little bit more complicated to answer is the point where we're trying to find the woman's near point. So her near point is not 25, as you can imagine. The near point 25 speaks to normal eyes. So what we can do now, we can try to figure out where the near point is. And that is based on a quick calculation here. So 1 upon f is equal to the power of the lens, yes? Which we kind of know that from the question. Okay? So the near point, all right, so to be able to can do this, let's see. So yeah, let's work out find the focal length. So 1 upon p is equal to f. So that should give us a value of 40 centimeters. Right, so this is the focal length of that particular lens that is added to her eyes. Now, let me just quickly check something here. If we were to use this, just want to check something quickly. Yeah, so I believe we'd have to use this equation to see what distance an object needs to be positioned, yeah, for her to be able to can see it perfectly, right? The 25 would be the image distance in this case, because that is kind of like where the image is cast in front of her eyes using the lens to, in a sense, be able to can then be able to can for her to be able to can see it actually. So that would be the image distance. Let's just see if we can manipulate this a bit and see if we can find out what the image distance would be, the object's distance rather. So 1 upon 40 minus 1 upon 25. Sorry, yeah. That is going to be 1 upon u. We can just drop this in our calculators and see if it gives us anything that makes sense a bit. All right, so I'm getting that U should be roughly negative 66.6 centimeters. I'm gonna have to check something pertaining to this one. And I don't want to kind of tell you the wrong thing, but I know, of course, you would need to obviously find your focal length. It's just now to see how we treat that other part of the information, all right? To figure out exactly the near point of her eyes. I'll definitely give this a check before we're finished. So I'm going to give you another question to try while I go ahead and try and check this one out for you. So go ahead, take this one, and then I get back to you pertaining to this one that I just did. By the way, all along, were you able to see me writing on my screen and everything?
Yes, sir.
Okay, I'm just checking because
Yes, sir.
Okay, okay. Were we able to answer that question? I'm just trying to find about that.
Yes, sir.
Yeah, good, good.
Yes, sir.
Yeah, what I'll try to do regarding
Sir.
the state. Yeah, go ahead.
Oh, so for the velocity,
Mhm.
I got 15.34 meters per second.
Yeah, that sounds like the answer, yes. Give me 1 second, I can find it in my book here. Say it again, 15 point?
34.
15.3, yeah. Yeah, man, that sounds like it. All right, what about the next part, yeah? I think it's the time. Time that the skater took from B to the ground. Were you able to get that?
Sir. Yes, sir.
Oh, you have.
1.43.
All right, just keep it to 2 decimal places, yeah? All right, 1 decimal place rather. So 1.4, yes? 1.4
Yes, sir.
seconds. Good, good, good. Are we all getting the same things, ladies?
I'm getting 1.56.
All right, but I'm not sure why. But I guess because you kept the velocity maybe as a large value for the 15.3 something. Maybe that's why, but well, then again, you don't need the velocity for this part. Let me just show you the working out on the screen quickly. So as you can imagine, we're dealing with energy. So change in potential energy is equal to your change in the kinetic energy. So from here so to here so, right? Overall change in potential energy is that the change in a height of about 12 meters, you know. So therefore, our general potential energy, when we do calculate it, the height that it changed is going to be 12 centimeters, or 12 meter rather. I kind of did a bit of shortcuts this, but you can go ahead and write it out the right way. So like, you know, so change in your gravitational potential energy is equal to your change in the kinetic energy. The m's can be cancelled out. So we can then restructure the equation to be square root of 2gh is equal to v. Then from here, so now, if when you find the square root of that answer, it gives you 15.3 meters per second. All right. Okay. Then now for this, now we use the equation that says S is equal to ut plus half a t squared. Because the thing is launching like this is how it's going to launch. Yes, there's not going to be any vertical velocity component, or we can say that the vertical velocity component is equal to 0 meters per second, while the horizontal component will be 15.3 meters per second. Yeah. So therefore, this equation can only apply to vertical motion, really. And so along the vertical, the initial velocity is going to be 0, right? Whereas the height is going to be 10. 0 times t gives you 0. So plus a half 9.8 t squared. 10 is equal to so t ends up giving you your 1.4. All right, I think that's the answer. All right, so they asked you to find the range as well. Sorry, not the range, but the horizontal distance r. So r is equal to v of x times t. So please, ladies, because this is a projectile motion thingy, you have to pay attention to that, all right? So this is your 15.3 times your 1.4, right? And that gives me 21.4 meters. They asked us to state two assumptions that you would make while doing the calculation here. I would assume that no energy is lost, okay, due to friction, and also we could say that there is negligibly air resistance. Again, I think those are the two assumptions that I could make. I don't know if you can think of any other assumptions, but if you can, then that would be good. All right. All right, ladies. What's your schedule like after, I mean, tomorrow evening? I don't know if you want to kind of meet up tomorrow evening or anything, so we can run through a few more questions. Let me know. Schedule packed tomorrow evening. When is the exam?
So like what time?
When is the exam again?
Next week. Not like the week coming, the week after.
About how much? About how much are me? May, how much is the exam?
May 8th.
May 8th. Okay. All right. I want you to screenshot this and attempt it on your own. Yeah. And I want to see the answers coming into my inbox or my WhatsApp so I can see what you're doing, please. Right? You have no other thing to be studying, right? I mean, there is no other subject you should be prioritizing at the moment. I would assume physics is the one that you should be giving all the attention and everything. Yes, and I'm also expecting persons to be asking me questions as well. All right. If you have any issues just surrounding anything at all, please do that. All right. So that's it for now, yeah? So that's it, girls. Take care now. Bye-bye, yeah?
Bye, sir. Thank you.
Bye, say thank you.
Bye, say thank you.
All right, no problem. Good.